Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we shall be discussing the solutions of the problems in Self-Test 7, Form B. And again, make sure you've worked on the problems, because if you have, I think this might be a fun type of module, because this is the closest we'll come to the type of problems where we'll be dealing with whole numbers. Let's take a look and see how this works, okay? Let's go over to the board and just tackle the problems in order. The first problem says to add 0.0806. And by the way, if you want to learn to read this, how do you read this? Without the decimal point, it would be 806. It's going to be tenths, hundredths, thousandths, 10,000ths. That's 806 10,000ths. But for brevity, I will just read it with point and have you figure out any other reading that you want. 0.83252. The 0 again, just to emphasize the decimal point, plus 0.0083. And again, remember, if you want to leave this 0 out, that's okay. But don't leave out any of these zeros. Leaving out one of these two zeros changes the column, the place that the 8 is in, and that changes the value. Okay? So what is the technique? Using the vertical form, we align the decimal points. Write the numbers so the decimal points align, because remember, as long as the numbers are in the same, in similar columns, they name the same denomination, and as long as they name the same denomination, we can just add them. If you'd like some symmetry here, you can put a 0 here, you can put a 0 here. Then we just do what? Once the decimal point is in place, we deal with this the same as if we had whole numbers. 2, 8, and 6 are 14, put down the 4, carry the 1. 8 and 2 are 10, and 1 is 11. Put down the 1 and carry the 1. 1 and 3 is 4, and 8 are 12. Put down the 2 and carry the 1. 8 and 1 is 9. The answer is 0.92142. And you see, the trick is, if you leave the decimal point out, this number is 8,060 hundred thousandths. This number is 83,252 hundred thousandths. And this number is 830 hundred thousandths. And you see, when we do the problem this way, as long as these numbers are modifying the same noun, we simply add the adjectives and keep the common noun. And you see, in this form, all of our adjectives are whole numbers. That's what I meant earlier when I said that this assignment will be very, very similar to what happened with whole numbers, provided we understand the decimal point concept. And just as with whole numbers, subtraction of 3 or more numbers requires grouping symbols. So problem number 2 gives you the 3 decimals, 8.23, 4.971, and 1.83, and simply groups them differently as we subtract. See, problem A says, take 8.23, subtract 4.971, and then from that answer, subtract 1.89. B says, first subtract the 1.89 from 4.971. And how do we know we do that first? Because when we have parentheses, what's the agreement? Everything inside the parentheses is done first. See, that came up a long time ago. But the point is that whatever is inside the parentheses is done first, regardless of whether we're dealing with whole numbers, common fractions, decimals, or mixed numbers. See, that part stays the same. Then whatever that answer is, we subtract that from 8.23. By the way, Form A is basically the way you would ordinarily do this problem on a calculator. You're simply subtracting the numbers in the order in which they appear. You see what's going to happen? You're first going to subtract 4.971 from 8.23. And the biggest trick here is to notice that you must put the 0 in here. You've got to say 1 from 0, borrow, and get the 9. See, if you leave that out and bring down the 1, that's wrong. And now the point I want to make is, from this point on, this is the same as if it was a whole number problem. I just line up the decimal point, and what do I say? 1 from 0 I can't take, so I borrow. 1 from 10 is 9. I have to borrow again. 7 from 12 is 5. I borrow again. I'm not going to do much of this, because after all, that was what we were doing in the second module. I just want to show you this has become a whole number problem again. You wind up with 3.259. See, that's the number that technically goes in here. Then what do we do next? We subtract the 1.89 from that. Here I could put the 0 in if I want, but I don't have to. But I simply subtract 1.890 from 3.259. Once the decimal point is in place, the problem is just like a whole number problem. The answer is 1.369. In typing the answers to the first addition, I left to blame the guy who did it. I don't like to tell people it was me. It was I. But basically, in typing, I put in an extra 1. The answer key to this problem is wrong. The answer in the answer key appears as 1.1369. That 1 shouldn't be in there. Okay? And part B is exactly the same kind of a problem, only the order of subtraction is different. This time, we're going to start with the 4.971 and subtract the 1.89. And again, you may or may not wish to put the 0 in here. You don't have to, because it's already serving there as a placeholder. Taking nothing from 1 is the same as bringing the 1 down, so there's no problem that way. At any rate, if you do that subtraction, you wind up with 3.081. Now you have to subtract the 3.081 from 8.23, and now you have to be careful. See, when you take 8.23 minus 3.081, now you have to remember that a 0 belongs here, because you do have to take the 1 from the 9 from the 0. In other words, you're going to have to do something like this. And at any rate, when you do this, the answer comes out to be 5.149. And the reason I'm rushing through these details is that once you've got the decimal point in place and have all the digits in, we have reduced a new problem to an old problem. We can ignore the decimal point and treat the problem just as if it were a whole number problem. All right? And now let's apply this to multiplication. Remember, we have addition, subtraction, and multiplication. Problem number 3 comes in 3 parts, and there's a reason behind each part. Well, hopefully. The first part says compute 8.23 times 3.01 times 0.04. And the reason for this is that in the text, we basically emphasized how you multiply 2 decimals. And the point is that by the associative property, to multiply 3 decimals, multiply 2 decimals, and then multiply the answer by the third. And which 2 do you multiply first? It doesn't matter, because multiplication is associative. You can group them any way you want. Commutative, you can change the order any way you want. And so when we do this problem, one way to do it is I could take the 8.23, multiply that by 3.01, then whatever answer I get, I multiply that by 0.04. All right? Now, part B starts out the same way, but after I've multiplied these 2 numbers, I then want to add 6.99. So in part B, I have what? The product of 2 decimals, which is again a decimal, to which I'm going to add a decimal. See, I've got addition and multiplication in the same problem. And in part C, compare C with B, and you'll notice that it's exactly the same problem as B, except that I've switched the grouping symbols. You see, in B, I first multiply the 8.23 by the 3.01, then I add on the 6.99. In C, I add the 6.99 onto the 3.01, and then multiply that by 8.23. You see here, the 6.99 is actually part of what's multiplying the 8.23. So now that you understand the problem, let's just mechanically go through the steps and get the answer. And again, nothing spectacular here. It's just a bunch of small steps, each of which was explained in the text, and we just put them together one at a time. For example, doing this problem in the order in which the factors appear, how do I multiply 8.23 times 3.01? What was the rule for multiplying? You multiply just as if there were no decimal points. Okay? We'll explain this in a later problem, but let's just do it mechanically now. Multiply as if the decimal points weren't in here. See, 1 times 823 is 823. Put in the row of zeros. 3 times 3 is 9. 3 times 2 is 6. 3 times 8 is 24. Add this up the same as if there were no decimal points. Then you count the number of digits to the right of the decimal point. There are 2 here and 2 here. That's 4 altogether. Starting at this end, you move the decimal point in 4 places. So we wind up with 24.7723. And how do we know that that's approximately right? Because this number is about 8. This number is about 3. 8 times 3 is 24. So we're in the right range here. Now we take this answer. See, we've already multiplied the 8.23 times the 3.01. And now we multiply that answer by our third factor, 0.04. And how do we do that again? Pretend the decimal point is not in here. Multiply as if this were 247,723 times 4, We multiply this out. You see the usual way, nothing new here. See what I'm saying here? 4 times 3 is 12. Put down the 2 and carry the 1. 4 times 2 is 8 and 1 is 9. See, 4 times 7 is 28. Put down the 8 and carry the 2. 4 times 7 is 28 and 2 is 30. Put down the 0, carry the 3. 4 times 4 is 16 and 3 is 19. Put down the 9 and carry the 1. 4 times 2 is 8 and 1 is 9. And you see that's exactly what we were doing in Module 3. Now we count the digits to the right of the decimal point. There are 4 here. There are 2 here. That means there are 6 altogether. When there's no decimal point, it's assumed to be after the digit furthest to the right. We now take that decimal point and we move it 1, 2, 3, 4, 5, 6 places. And we put a 0 in front to emphasize the decimal point. This is not in here. The answer is what? 0.990892. And you can leave this 0 out if you want. If you want to, you can put a whole bunch of zeros out here. You see, once this decimal point is in place, adding on none of the denomination doesn't change anything. What you do have to be careful about is don't delete or insert zeros between digits. Because if I leave this 0 out, that moves the 8 into the thousandths place rather than in the 10,000ths place. Now, to emphasize that I could have multiplied in different orders, what I've done next for you is I decided to first multiply the 3.01 by 0.04. See, 301 times 4 is 1204. 4 decimal digits. I move the decimal point 4 places to the right. That gives me 0.1204. I take that answer. I multiplied that by 8.23. I'll spare you the details, but omitting the decimal points, you see what I do? I multiply this the same as if it were a Module 3 problem. I get the answer, 990,892. Then I count the number of decimal digits, 1, 2, 3, 4, 5, 6. I then count off 1, 2, 3, 4, 5, 6 places. And lo and behold, I have the same answer as we had before. Which is the right way? Either way. All right? And sometimes you'll find groupings that are easier to handle. In other words, if you see a 4 multiplying a 5 someplace, even if it's in a different order, 4 times 5 is 20, it's easy to multiply by 20. If there's another 5 later on, 20 times 5 is 100. To multiply by 100, you just tack on 2 zeros, or better still, move the decimal point 2 places to the right. So you do these things in whatever order you want. Now, Part B says, multiply 8.23 times 3.01. Remember, everything in parentheses is done first. Then add on 6.99. Well, this is easy, because in doing Part A, I already multiplied 8.23 times 3.01 to get 24.7723. Now, how do you add? See, to add, you simply take the 2 numbers. See, this is gone now. The product of 2 numbers is a number. So this is the number. I add 6.99 to it. Now I just do what? The regular addition problem, line up the decimal points, add the same as if there were no decimal points in here, and the answer is 31.7623. And now Part C, which may look hard, turns out to be perhaps the easiest of the 3. You see, what happens in Part C is that we're first told to add the 6.99 to the 3.01. And if you do that, you find that, well, do it in terms of money. $3.01 and $6.99 would be $10. So the 8.23 is going to be multiplied by 10. What's the rule for multiplying by 10? Take the decimal point and move it what? 1 more place to the right. That moves the decimal point from being between the 8 and the 2 to between the 2 and the 3. So the answer is 82.3. Okay? That's all there is to it, just a straightforward drill. Now, the point is, I want to emphasize to you that no matter how many digits there are in a decimal, if all you want is a quick approximation, we can still do this the same as we always did. Read the instructions here. It says, by rounding off each factor to the nearest whole number, estimate the product and get a load of this, 6.234567 times 7.89765204. I may have made a few copying mistakes compared with what's in the text, but based on what I'm asking to do in this problem, it doesn't matter. See, this looks scary, but what does the instruction say? The instruction says round off each of these to the nearest whole number. See, 6.2 is between what? 6 and 7. See, it's more than 6. See, it's between 6 and 7. But because this digit is a 2, we're closer to the 6. Is that correct? And 7.89 is more than 7, but less than 8. And because this is an 8 in the digit next to where we're rounding off, 7.89 to the nearest whole number is closer to 8 than it is to 7. So this number rounds off to 6. This number rounds off to 8. So the answer to this question, lo and behold, is nothing more than 48. What we're saying is an estimate. It's not the right answer, but an estimate is 48. In fact, notice that 7 times 8, which is 56, would be too big to be the right answer. And since 6 is less than this number, and 7 is less than this number, and 6 times 7 is 42, whatever this answer is, it's what? More than 42, less than 56, but close to 48. And from that point on, I don't care what happens in this problem, because I'm just looking for an estimate. Do you see how this works? Okay. Now I'm going to review how we multiply with you. And to make the multiplication easier, in problem number 5, I do the hard part for you. Well, the relatively hard part for you. I actually multiply out the 452 times 314. Hopefully, I did it right. If I made a mistake, who cares? Because all I said over here is suppose we're given that this is true. Hopefully, it will be true. But as far as this problem is concerned, this is a true statement. And based on this, I'm saying, without doing any more work, how much is 4.52 times 31.4? You see, what I want you to get the feeling of is that when you multiply two decimals, you pretend the decimal points are not in here. Well, that's exactly what this would give me. Then what do? You count the number of decimal digits to the right of the decimal point. There are 2 here and 1 here. That's 3 places. So you now move the decimal point in 3 places, and the answer is what? 141 and 928 thousandths. 141.928. And to see why that works, remember, how do you read this number? Without the decimal point, the adjective is 452. There are 2 digits to the right of the decimal point. That makes it hundredths. So this is 452 hundredths. This number without the decimal point would be 314. There's 1 digit to the right of the decimal point. That's tenths. So we're multiplying what? 452 hundredths by 314 tenths. How do we multiply numbers? We multiply the adjectives. That's where the 452 times 314 comes from. Then we multiply the denominations, hundredths times tenths. That gives me thousandths, and that's where I get the fact that I moved the decimal point 3 places to the left. To divide by 1,000, see, thousandths. I'm dividing by 1,000. Per 1,000, I move the decimal point 3 places to the left. And part B just gives me one that usually is an eyesore, but again, without even reading this, if I leave the decimal points out, remember these zeros don't mean anything once the decimal point is left out. The decimal point only affects what noun the 452 is modifying. What am I doing in this problem? Without the decimal points, I'm multiplying 452 by 314. We're given in this problem, see, given that 452 times 314 is 141,928. See, given that, I bring this down here. Now what do I have to do? Find the denomination. And how do I do that? I count the number of digits to the right of the decimal point. 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4 here. 6 and 4 are 10. That means I have to move the decimal point 10 places to the left. The only trouble is I have what? 1, 2, 3, 4, 5, 6. I only have 6 digits. So what do? To indicate that I still have 4 more places to move the decimal point, I pre-annex, I guess that's the word. See, I annex at the beginning 4 zeros. And the answer to this problem is what? 0.0000141928. Okay? I don't even have to know how to read this number. It's just a mechanical process. And now, with those 5 problems as background, we come to the hardest part. The hardest part is, once you know what to do and how to do it, recognizing when to do it is even harder. See, it's one thing to know that 9 times 3 is 27. It's another thing to know without anybody telling you that you're supposed to multiply 9 by 3. Now, let me show you how that works over here. Watch problem number 6. Problem number 6 says, at $29.99 each, what is the cost of 8 shirts? Does any basic operation appear explicitly here? Is anybody telling you to add to multiply, divide, or subtract? No. See, the hard part of this problem is you have to figure out that step for yourself. Once you figure out that step, then one of the techniques that we used in the first 5 problems will help you solve this problem. See, how are we going to analyze this problem? We want to find the cost of 8 shirts. Each shirt is $29.99. So 2 shirts would cost $29.99 twice. 3 shirts would cost $29.99 3 times. In short, what do we want? The 8th multiple of $29.99. You see, to solve this problem, we're simply going to take what? $29.99 8 times. And we do this, and we get $239.92. By the way, you can get this answer and still have no feeling for this. This is a typical advertisement, isn't it? $29.99, because they want you to hear 29. What is $29.99 to all intents and purposes? It's $30, isn't it? Look how much easier the problem sounds if you say each shirt costs $30 and I'm buying 8 of them. You say, wow, the answer is $240. You don't buy that many, right? But it doesn't matter. Watch how we can solve this by the distributive property even better. Isn't $29.99 the same as $30 minus a penny? See, so what we do is what? We multiply the 8 by the 30, then see 8 times $30 is $240. Then what do? Subtract 1 cent 8 times. And that gives you what? $239.92 right away. Do you have to be clever and do the problem this way? No. You can do it the other way. But do you see what number sense does for you? You're not going to get cheated badly this way. If you have a number sense, you estimate what the cost is supposed to be. If this is rung up at the cash register and by mistake they punch in a 9 instead of an 8, you're going to see that the price is too high because the price was supposed to be what? Just a little bit below $240. See, learn to do things that way. Problem number 7, same kind of thing. The problem is longer. The statement of the problem is longer than the solution. Let's look and see what's happening over here. You're told that a gallon of paint paints 8 walls. You have to paint 28 walls. The paint comes only in a 1-gallon size and costs $10.16 per gallon. And the question is, how much must you pay for the paint to do the paint job? Is that a realistic enough problem? I think so. Well, how do you do this problem? Well, the $10.16 per gallon tells you that to find out how much you have to pay for the paint, all you have to do is multiply the number of gallons by 1016. Unlike the previous problem, where I told you how many units you were buying, in this problem, you have to do another step first. You're going to have to walk and chew gum at the same time. You see, instead of telling you that you need 5 gallons or 6 gallons, all I'm telling you is what? You have 28 walls to paint, and each gallon paints 8 walls. Don't be fancy about this. Do it the baby way if you want. See, if 1 gallon paints 8 walls, 2 gallons will paint 16 walls, 3 gallons will paint 24 walls, 4 gallons will paint 32 walls. In other words, we're counting the gallons as multiples of 1, but the walls get counted as multiples of 8. Same stuff as we're doing in chapter 3. Well, look at, we have what, 28 walls? 28 is more than 24, but less than 32. That means we need more than 3 gallons, but less than 4 gallons. But the paint only comes in 1-gallon sizes. So the fact that we need more than 3 gallons says that we have to buy at least 4 gallons. So we go out and we do what? We pay $10.16 4 times. And $10.16 times 4 is $40.64. See, notice that if you know how to do this, but you can't figure out how many gallons of paint you need, what's the sense of knowing that $10.16 times 4 is $40.64? By the way, if you want to do this without the baby way of counting, you're saying what? There are 28 walls. Every gallon paints 8 walls. 8 goes into 28 3 times with a remainder of 4. That's 4/8, which is 3.5. That says you're going to really need 3.5 gallons, doesn't it? But you have to buy 4. That's not such a bad thing, because what this says is you pay for 4, you get the job done. That means you're still going to have a half a gallon left, and every so often you might want to touch something up. In fact, lots of times people deliberately, when they get paper or paint, buy extra in case that particular color or style goes out of stock. You'll always have a replacement that way. But better to have a little bit too much than not to have enough. Okay? What other kind of applications do we have? How about something as simple as balancing a checkbook? That's what problem number 8 says. And by the way, when I say simple, I'm not trying to make fun of you if you have trouble balancing the checkbook. I mean simple in concept. And just because something is simple doesn't mean that it's easy for you to do. In the Sherlock Holmes stories, when Holmes says to Watson, "Elementary, my dear Watson," it takes 42 pages after he says elementary to show why the solution worked. So when we say that something is simple, it means that it's conceptually not difficult, but you still have to understand the concept. So let's see if we can go through it together. You have $62.37 in your checking account. Now you deposit your paycheck for $172.97. You then write checks for $28.37, $46.27, $53.69, and now you want to know how much money you still have in your checking account. Well, some people just assume that until the check is cashed, they haven't lost anything yet. Now, I'll mention that in a moment. But basically, you see, the idea is you first have to figure how much money is mine and how much have I given away. And there's going to be a couple of ways of doing that. And by the way, as we go in more and more for automated tellers, people decide they don't have to keep a good balance because the bank will do it electronically for them. Remember, a check cannot be deducted by the bank from your checking account until that check is cashed. You know, if you go to the bank after you've written checks, say a week later, and you get your balance, you have no way of knowing whether all of your checks cleared or not. That balance may be while somebody hasn't cashed in one of your checks yet. So you want to keep an accurate record. And then when the statement comes from the bank at the end of the banking period, then you can correlate your findings with theirs. I like to use the rule that if the bank doesn't bother me when I'm overdrawn, I won't bother them when I'm underdrawn. But it doesn't work that way, I'm afraid. But let's just go and do the problem. As I say, don't rely on the automatic teller. The best thing to do is what? First of all, find out how much money you have. Simply take the money that was in the bank before you deposited your check, now add the deposit to that. And by the way, that's another tough thing. In certain states, the banks take several days before they credit your account. In other words, you can put that $172.97 in there, write a check, the check goes back to the bank, gets cleared, but they haven't credited your $172.97 yet. That's another little wrinkle that you have to worry about, but that has nothing to do with the math class. That just has to do with things to watch out for. Anyway, you take the amount you put in plus the amount you already had, and you add those up. And notice, I have to make the judgment to add. No one said add those two. I have to have enough feeling for the problem to say, hey, this is what I already had, this is what they're giving me on top of that, so I add the two together, and that's what I have. Now what happens? Every time I write a check, I should subtract that amount from what I have in the bank, because once that check gets cashed, that's how much is going to be deducted from my account. So one way to do this is start with the $235.34, subtract the first check amount, which is $28.37. That tells you after the first check is cashed, you're going to have $206.97. Now, from that amount, subtract the value of the second check, $46.27. That tells you that when that check is cashed, you're going to have $160.70 left. Now, from that, you subtract the value of the third check, $53.69, and that tells you that when the third check is cashed, you're going to have $107.01 left. And by the way, is it possible that the checks may get cashed in a different order? Yeah. In other words, you don't know that this is exactly the way things are going to happen. All you're saying is that by the time all three checks get cashed, this is going to be my balance. And by the way, if you don't like to keep subtracting, there's more than one way to reason through a problem. Look, couldn't you add up all the money that you're spending? Couldn't you say I'm spending this amount, and this amount? So altogether, see, and how do I add here? Same as we were doing before. Line up a decimal point, add the same as if the decimal point wasn't in here. Altogether, I'm spending $128.33. I had $235.34 in the account. So I subtract what I'm spending from what I already had left, and that difference must be what's left in the bank. In other words, if I take what's left, add that to what I've spent, that should add up to what's in there now. And again, beware of such things as charges for writing checks, service charges, and the like. Those are deductions that you may not know about. The bank knows about them, but you may lose track of that. So be careful about these things. These problems I'm giving you are very simplistic. They're just meant to show you the basic principle. I have my own little trick for saving money. It doesn't work because I know what the trick is, so I cheat. But basically what I do with my checkbook is if I have $60 in change, I pretend the change isn't in there. And if I deposit $172 plus change, I pretend it was just $172. So now when I add the thing up, I'm giving myself credit for less money than what I have. Then when I have a check for, say, $28.37, I round it up to the next dollar. I subtract $29, and see what I'm doing that way? I'm hiding 63 cents. Then the next check for $46.27, I pretend that was $47. Then the next one that was $53.69, I pretend that was $54. When I get all through subtracting, my checkbook would then show a balance of what? $104. How much money is in there? $107.01. It's a heck of a thing to try to reconcile my checkbook, but the thing is that every so often I find out that what? I have a little bit extra in there that I didn't expect to have. And if you don't like to fool with the checkbook that way, that's another interesting psychological thing that has nothing to do with mathematics. At the end of every day, just take out all the change that you have in your pocket and put it into a container. And start the day with fresh bills and no change. And you'll be amazed at the end of a month how much money you will have saved up that somehow or other you never save when the change is in your pocket. You see something for 23 cents, you're not going to break a $10 bill to get it usually. But if you have a quarter, you say, what the heck, I'll spend the quarter. So notice again that math plus psychology is a heck of a lot more powerful than math or psychology. If you combine subjects, what emerges is something more powerful than either of the subjects separately. And let's just keep on going this way. Some of the problems we're going to do here are all more of the same. Problem number 9 says you have $225 to spend on clothes. That's the same as saying you have a clothing deposit. Now it says you buy 6 shirts at $12.75 each. That's the same as writing 6 checks, each for $12.75. See? And you're buying 3 pairs of slacks for $14.99 each. And you're buying 4 ties at $8.78 each. And the problem says, how much is still in the account left to spend? See, now you're going to put several problems together, several computational techniques together. You're first going to find out how much money you spent on the shirts, and how will you do that? That was like a previous problem. You're going to take the price per shirt and multiply that by the number of shirts. Then you're going to find out how much you spent for the slacks. How are you going to do that? You're going to take the price per pair of slacks and multiply that by the total number of pairs of slacks. Then you're going to find out how much you paid for the ties. And how are you going to do that? You're going to take the $8.78 per tie and multiply that by the number of ties, which is 4. So altogether, on the shirts, you spend $12.75 times 6. See, no one is telling you to multiply. You have to figure that out for yourself. You multiply the 6 by the 12.75. You multiply the 3 by the $14.99. You multiply the 4 by $8.78. And what you find is you've spent $76.50 on the shirts, $44.97 on the slacks, and $35.12 on the ties. So how much did you spend altogether? You just add up these amounts. And how do you add these amounts? That's just adding decimals. You align the decimal points. Once the decimal points are lined up, this is like a whole number problem. You just add up 2 and 7 are 9. 9 what? 9 cents. 1 and 9 are 10, and 5 is 15. 15 what? 15 dimes, 15 tenths. Put down the 5 and carry the 1. See, 5 and 4 are 9, and 6 are 15, and 1 is 16. Put down the 6 and carry the 1. And you see the important point here is when you get this $156.59, first of all, nobody is telling you to add. You're figuring that out for yourself. See, that's what the rest of this course is going to deal with once we finish decimals. Word problems. How do you use the math? You're going to have a calculator to do the math for you. You're going to have to talk to that calculator and tell it what you want done. Okay, but that comes up in Module 9. We'll talk about that later. Now I've got the $156.59. What is that? That's how much I've spent for clothes. How much more do I have left to spend on clothes? Well, whatever it is that I can add on to $156.59 to get $225, And more traditionally, how do I do that problem? I subtract the $156.59 from $225. That gives me what? $68.41. That's how much money I still have left. Look what I did in this problem. Multiplication, addition, subtraction, and nobody told me which of these operations I was supposed to be doing. You see, I had to know what to do. See, the first few problems drilled me to see if I knew how to do the operations. The rest of the problems are saying, okay, now that you know how to do it, do you know when to do it? That's what it's all about. And with that in mind, let's go on to the very last problem. Almost as important as miles per hour now has become the environmental protection type things and the gas efficiency, what we call MPGs, miles per gallon, and every car now comes equipped with a sticker that tells you how many miles per gallon you're supposed to get. How they arrive at that figure is sometimes suspect. That's why some states are much stricter than others in telling you how to interpret that. But basically, we use it as a relative measurement. So suppose the sticker on your car tells you that you should average 21.4 mpg. That's miles per gallon. What that says is, on the average, for every gallon of gas you use, you should go 21.4 miles. That's kind of ridiculous. If you're stuck in traffic and you're idling, you're going to go 0 miles per gallon. And if you're moving on the highway, the chances are you might be getting better than 21.4 miles per gallon. You mustn't expect that you're going to get this constant rate, this steady rate of 21.4. That's just an indicator, okay? At any rate, based on this, the question asks us, to the nearest mile, how far can you expect to go on 7 1/3 gallons? In other words, if you can go 21.4 miles per gallon, if you can go 21.4 miles on 1 gallon, how far should you be able to go on 7 1/3 gallons? And by the way, since it's much easier to think in terms of whole numbers than in terms of mixed numbers and decimals, why not do that? Why don't you say to yourself, wait a second, 21.4 miles per gallon. That's more than 21 miles per gallon, but less than 22 miles per gallon. And 7 1/3 gallons, that's more than 7, but less than 8. So let's make an estimate now. If I went 21 miles per gallon on each gallon, on 7 gallons I would go 21 miles 7 times. 21 times 7 is 147. So obviously then I'm going more than 147 miles. On the other hand, if I got 22 miles for each gallon of gas and I had 8 gallons, 22 miles 8 times is 170. That's not 172. Is that 176? 8 times 2 is 16. But what's 4 miles to a philosopher and bad driver? We still get an estimate, okay? That's what's nice about estimating. If you're off by a little bit, you say, big deal, it was just an estimate. It's when you say the answer is exact that it's embarrassing to be wrong. Do you ever see people, you say, what's the time? They say it's around 5:23. They don't say it's around 5:30. They say it's around 5:23. You can always tell they're wearing a digital watch when they say that. But it's around 5:23. It's around 176. No, you round off here. We don't have to be that exact. But let's be precise anyway. The point is, what this tells you is, at 21.4 miles per gallon, on 7 1/3 gallons, you're going to go more than 147 miles, but less than 176. Some people get very sloppy. They say, look, didn't he say he only wants this thing to the nearest mile? So why work with all these messy numbers? We'll just round off. To the nearest mile per gallon, 21.4 rounds down to 21. And to the nearest gallon, 7 1/3 rounds off to 7. So why don't we round off the answer and say it's 21 times 7, or 147? And that could be a guess. Let me show you what the danger of that is if you round off too soon. And by the way, once you have a calculator, there's no advantage in rounding off too soon. With a calculator, the trick is don't round off until the very last step. When you're doing things by hand, the stuff gets so messy that it's a nuisance to keep track of all these decimal digits, so you usually round off as soon as you can. But a good rule of thumb is the later you round off, the less errors you're compounding. I'll show you in a little while what errors you're compounding over here when you round off. But what is the exact answer? No matter what these adjectives are, what is the theory behind this problem? You multiply the miles per gallon times the number of gallons. instead of 21 times 7 or 22 times 8, it's going to be 21.4 times 7 1/3. Now, there's lots of ways I can do this problem. The way I prefer to do it is to emphasize our second language technique. Since I feel comfortable with common fractions, and I'm not going to use my calculator because I don't want you using yours yet, I'm going to do the problem in a way that makes me the most comfortable. Well, it doesn't really make me comfortable, but it's okay. See, I take 21.4. Without the decimal point, that would be 214. 214 what? There's one digit to the right of the decimal point, so the label is tenths. So 21.4 is 214 tenths. 7 1/3 is what? 3 times 7 is 21, plus 1 is 22. That's 22 thirds. And by the way, if you don't like my method for doing this, do it this way. Say 21.4 is 21 4/10. Then you can say 10 times 21 is 210, plus 4 is 214 over 10, and you get the same answer. Now we take what do? We multiply the numerators. See, that's where the calculator is going to help us. When we want to multiply 214 times 22, we won't have to do something like this to get 4,708. We'll just punch it into the calculator. But the thing I'm leading up to is the calculator won't give us the 4,708 unless we know enough to have it multiply 214 by 22. Then 10 times 3 is 30. So as an improper fraction, the answer to this problem is 4,708 over 30 miles. And by the way, again, if you wanted to, you could have said 2 goes into 10 5 times, 2 goes into 22 11 times, and you could have written the problem as what? 214 times 11 over 5 times 3. But the calculator doesn't care whether you reduce or not. You can do that, but let's just finish the problem now. Now we divide the 30 into the 4,708. When we do that, we see what? 30 goes into 47 once. See, this is now, what, a whole number problem. We subtract, we get 17, bring down the 0. 30 goes into 175 times. 150 from 70 is 20. We bring down the 8. 30 goes into 208 6 times. 180 from 208 is 28. So what do we have over here? 156 whole miles and 28 thirtieths of what you need for the next mile. Isn't 28 out of 30 more than half? And the problem says round off your answer to the nearest mile. See, we had 156 and 28 thirtieths. So what do? We round that off to 157 miles. And that's about how far we can expect to go. Give a little, take a little, depending on the mileage. But here's the thing I wanted to show you. When we rounded off over here, we said, okay, this rounds off to 21, this rounds off to 7, so the answer apparently should be 147. Let me show you what we were missing when we did that. See, when you multiplied the 21 times the 7, remember what we said about mixed numbers or decimals? When you're multiplying the sum of two numbers, each of which is a whole number plus a fraction, don't you have to take all possible pairs? See, the 7 has to multiply the 21. See, the 21 multiplies the 7. The 21 also has to multiply the 1/3. The 0.4 has to multiply the 7. And the 0.4 has to multiply the 1/3. You see, when we just took the 21 times the 7, we were throwing away all of this. Well, look, 0.4 times 7 is 2.8. That's almost 3, isn't it? You're throwing away almost 3 miles that way. 1/3 times 21 is 7. You've thrown away another 7 miles. 0.4 times 1/3, that's, we won't get into that, but roughly, see, 0.3 times 1/3 would be 0.09. Without getting into a big hassle over this, 0.4 divided by 4 would have been 0.1. This happens to be 0.13, but who really cares? The thing is, if I add this up, what do I get? 9.93. In other words, I threw away 9.93 miles, which to the nearest mile is 10 miles. You see, by rounding off too soon, I threw away numbers that were affecting other numbers. And by rounding off too soon, I actually threw away what? 10 miles. And 10 miles could be a significant amount. At any rate, this completes our discussion of Form B of Self-Test 7. Next time we're going to get together and again do fractions, but this time the fractions will be only with respect to the operation of division. And we'll talk about we'll talk more about that next time. And until that time, keep studying hard, have fun, and stay young.